the grade 12 physical sciences class with Mr. Phil Young. We are going to look at the Doppler effect today. And the Doppler effect is basically just the effect of velocity on the frequency of a wave. Now, before we can carry on, let's take a look at some grade 10 revision. We have this over here, v equals f lambda. Then we have f is 1 over t. Now, v equals f lambda, that's your speed, is equal to frequency multiplied by the wavelength. Speed is in meters per second, frequency is in hertz, and your wavelength is in meters. Period is in seconds. Now, just a little revision from grade 10 that your frequencies is waves per time, and your period is times per wave. Alright, so looking at this, this specific formula up here, we can tell that frequency is inversely proportional to the wavelength. And that will tell us then that frequency is directly proportional to the pitch or the tone. Pitch and tone being the highness or lowness of a note. So the higher pitch, the higher it is. The higher it is, and the lower pitch will be a lower sound. Now, to the grade 12 work. We have here a listener, L, listener, on the left, and we have a source of the sound on the right. The source can be anything. It can be an ambulance, it can be a train, it can be a factory, it can be a crazy person screaming, it can be anything. It can be me speaking. So now, what happens in this Doppler effect situation is that if the source, or the listener, but we're going to talk about the source now, if the source were to move closer to the listener, what will happen is this. The sound waves that originally would emit at a nice spherical constant type of sphere around the source will now actually be compressed. Let's see if I can draw this. Will sort of be compressed in the direction it is moving. So when this sound source comes close to the listener will receive a pitch or hear a pitch that is higher in frequency, because there is a lower wavelength. Earlier we just spoke about how these two are inversely proportional. So as this moves closer, if you take a look here, we have this distance over there and that distance over there. So what happens is it will shorten the wavelength. So you see here, which will then mean that we have a higher frequency, which means a higher pitch or a higher tone. All right. So that is what this whole section is about. Now, obviously, if that moves this way, it'll be vice versa, right? So then the person will hear a deeper, you have elongated wavelengths, which will mean higher wavelength and lower frequency or pitch. So the opposite is absolutely true as well. So the formula goes as follows. The formula we are going to be using, it is the frequency heard by the listener is equal to some things over, or in a fraction form, multiplied by the frequency emitted by the source, the sound source. Right, so on this fraction over here, we can have a plus minus and then a minus plus. I'll tell you why I'm doing that now. And we have the speed of sound. The speed of sound should be small v, speed of sound. And then we have speed of the listener and the speed of the source of the sound. So that is the formula. Let me put it on the right here quick. So what we can do is just list it like this, FF, VVV, like when you do your calculations in the exam or the test, or for homework. So we have frequency listener, frequency source of sound, velocity of the listener, and velocity of the sound, and speed of sound in general, right? All right, so we have FL, which is the frequency heard by the listener in hertz. We have Fs, which is the frequency emitted by the source in hertz. We have the velocity of the listener, we have the velocity of the source, and we have the speed of sound, which is 340 meters per second, unless otherwise stated. Now let's take a look at this formula, and let me explain how to choose now. You have to choose which time it will be a positive and which time it will be negative. Now if it's positive at the top, it will be negative at the bottom. And if it's negative at the top, it will be positive at the bottom. That's why I do it like all funny like that. So let's just say a husband and wife, now they see each other after long absence, and absence makes the heart grow fonder, so they'll have a positive experience, right? But when they go away from each other, they will have a negative experience, negative emotions. So that's how you can remember which way is which. Very helpful. put a like my video and subscribe because of this lovely thing I just drew here. Thank you. Right, so let's dive right into it. Now, let's just say we had a listener, a person, and there was a car, and the car emits a sound at a frequency of, let's just say it is 500 hertz. The car is hooting at 500 hertz, and there's a person, and he is just standing still, and the car is moving towards the person at a velocity of, let's just say, 20 meters per second. What will the listener hear? What frequency will this listener hear when the car is coming towards him and it's hooting? So what will he hear? Now, first of all, we just go F, F, V, 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 triple V, right? And we go alphabetical, L, S, L, S, and we put in some values and just plug it in. Now, frequency of the learner, that's you. The listener is, we don't know, that's what we're trying to find out. The frequency of the source of sound is 500 hertz. The velocity of the listener, is it moving? No, not moving. And velocity of the source is 20 meters per second. The unit is correct, so I'm just put a 20 there. And velocity of sound, speed of sound is just 340. Like I said earlier, just know that, unless they say otherwise. So let's plug it in. Right. Frequency heard by the listener, we have speed over speed. Oh, is that a plus, minus, or minus, plus? Well, we just heard a few moments earlier that if they're going towards each other, because the married couple hasn't seen each other, they're happy. Okay, that's what we know. And then we have velocity, and then alphabetically LS. And then we put your frequency of your source. It's basically just multiplied by. Now, let's plug in some values. Speed of sound, 340. Plus minus. Velocity of the listener, we just have a 0. And speed of the car, was it a car? Eh? Yeah, car is 20. See, we don't put a plus or minus here. The direction we choose the positive and negative values before. So we just take that 20 meters per second, or that 20, velocity. We don't put a plus or a minus in here. We just leave it as is. Oh, no. Now, as you can see, straightforward maths. We just plug that in our calculator. Let's see what we get. But before we see what we get, will the frequency heard by the listener be higher or lower? Think about that while we write down the answer. We get 531 hertz. As we can see, the reason is because the sound source, or the source of the sound, is moving closer towards the listener, and the sound waves get compressed, causing a shorter wavelength, which means a higher frequency, which means a higher pitch or higher sound. Cool. Now, what if the vehicle were to move in the exact opposite direction, it's moving right, and the listener remains the same? So the only thing we change is that it's going this way, away from the person. Let's see. I'm just going to quickly just substitute in, and let's take a look. So all the values remain the same. The source of the sound is the same. The velocity of the listener, the velocity of the vehicle or the object, the source, and also the speed of sound remains the same. The only thing that changes is these signs. They swap out, because you're moving away from. And remember, when they move away, they get sad, and that's negative. It's a negative emotion. So that's the only thing that changes. Oh, obviously your answer will also change. So we have 472 hertz, which is a lower sound or lower pitch, which will result in that. Yeah. Right, down to the what? Down, up. Next question. So in our next situation, we have here Chopper, and he's running towards. Just hold on. Right, so running towards the sound source, which can be anything. It can be a building. It can be a helicopter. It can be a person shouting. It doesn't matter. So this chopper is running towards the sound source at 6 meters per second. What will this chopper hear? What will the frequency be that the chopper hears this sound at? Because it's emitting at 500 hertz, but will it be higher or lower than 500 hertz? It will be higher because they're moving towards each other. If they move away from each other, then it will be a lower frequency. So let's take a look. So I just plugged in my values here. We want to know what the frequency what frequency is heard by the listener. We know the frequency from the source is 500 hertz. The velocity of the learner is 6, of the listener is 6, and the velocity of the source is 0. It's stationary at this time. And the velocity of sound is, or the speed of sound is 340. So let's plug it in. We have frequency heard by the listener is equal to some fraction that's going to multiply to the frequency of the source of sound. So are they going towards each other or away from each other? Towards, so they're happy. And then at the bottom we just put the negative. And then we have speed of sound, speed of listener, or velocity of listener, velocity of sound. Let's go alphabetical, straightforward. Let's plug in. Right, there we go, plugged in. Right over there. So we have the speeds of 340 and 340 of sound. And we, at the numerator, we're adding that 6 meters per second of the listener going towards the source, and then at the bottom we have a 0 speed for the source. Just plug this in a calculator and see what we get. We said it's going to be higher, right? So let's take a look. We get 508,82 hertz. Makes sense, eh? Because they're going towards each other, so the frequency will always be higher. All right, let's take a look at the next example. In our third example, we have a teacher in the corridors shouting at girl Kelsey because she doesn't have a blazer on. And so she got a fright and ran away. She's running away at a nice constant, 8 meters per second, almost Olympic level. And this teacher on the left here is saying, blazer, no corridors, like a monotonous, like drawn out type of constant frequency. So the question is then, the teacher is remaining stationary. Kelsey is running away with a nice long nails, and running towards the right. And we state here that the frequency at which Kelsey hears is 0.98 times what the source of sound is, because she's obviously running away, right? Not running towards the source. So we must now calculate what is the oh, we have to work this out. Okay, let's scratch that. What is the velocity or the speed of Kelsey, of the listener? Okay, just to reiterate, the teacher is remaining still, shouting at some type of frequency, at some amount of frequency, and the sound that Kelsey hears, the listener hears, is 0.98 times the frequency of the source, because she's running away. So how fast is she running, Kelsey? Let's hope it's not like very fast. Let's take a look. So the frequency of, well, let's start at the bottom here. We have 340 meters per second. That's our speed of sound. The velocity of the source is 0. The velocity of the learner, or listener, I'm stop saying that, is, we don't know. That's actually what we want. That's what we want, right? But the frequency of the source is unknown, but the frequency heard by the listener is 0.98 times that source. So let's see. Why don't we make that x, and this then 0.98x. Very important. They sometimes throw these little mathematical things at you. So write down a formula. Let's go. So we have frequency heard by the listener is equal to a fraction times our frequency of sound, and they're going away from each other, right? They're going away from each other. And speed of sound is 340. And I should probably write the formula in. Right, there's the formula. So VL is what we want, and the VS is a 0. VL is also, we decided it to be 0.98x, and VS we said is just x. So now it's just down to mathematical, solving it mathematically. The important part was this, to see that, or to put that down as your values, to assign these values to your VL and VS. The rest is just straightforward maths. All right, let's take a look. So on the right we have one term, on the left we have one term, so we can just divide through by the x's, right? So I'm going to divide both through terms through with x, and I get 0.98 is equal to 340 minus VL over 340. Now remember, the numerator is like in a bracket, and the denominator also, so just be careful messing with that. So let's multiply all terms through by 340. And we get 333,2 equals 340 minus VL, and minus VL is then equal to negative 6,8. So the velocity of the learner is then 6,8 meters per second away from the sound source. Cool, eh? So here it is. So that's how fast Calzi was running. That's pretty fast down the corridor. Not putting a blazer on in the corridor. And yeah, anyway. All right, so that was the basic calculations there that you can look out for. Obviously, doing some past papers can get you more prepared. So let's look at a few applications. Now, where can Doppler effect be used in real life? So we have some uses where the heartbeat of an unborn child can be determined by sound waves being reflected off the child's heart, and there's a change. You can work out that change, and that change will be the heartbeat. And also then the rate of blood flow, they use a Doppler flow meter as the red blood cells move away from this Doppler flow meter device. You can determine a change in displacement, etc., and you can find out how fast the thing is moving. All right, so let's take a look at the next application, which is for light. So the Doppler effect and light. Now, remember, light can be a wave or a particle, like dual nature property of light. Anyway, we can deal with light as a wave. And let's take a look here from grade 10. We can take a look there. We have wedge above, which is the color of light. Red being lower frequency and higher wavelength. Remember, they're inversely proportional. And violet, blue indigo violet, being a higher frequency and a lower wavelength. So I just did a little area. The more you go to the right, the higher the frequency, and the more you go to the left, the higher the wavelength. Now, they can reverse the whole color scheme just in the opposite direction, and obviously then the opposite will be true. Just remember, red has the highest wavelength or lowest frequency. If you just remember one of them, you can remember everything else. So if you know that violet has the highest frequency, then you know it has the lowest wavelength, and therefore red will have the lowest frequency and the highest wavelength. So if you just know one of these, like red, a red wave, I don't know, just think of something, and then the rest you can just figure out. All right, so we have two people and we have a light source. This is Dave, and this is Daniel. And this light source is being thrown at Daniel. Now, but this has to be like at a very fast speed. But anyway, so what happens is, as this light source, that is the middle part, the things around it is the, trying to illustrate the waves of light. Oops. Anyway, it's being thrown there. So what's happening to Dave is he is seeing like a longer wavelength, a higher wavelength, and Daniel will see a lower wavelength, which means he will see a higher frequency, which means Dave will see a lower frequency. And in terms of light, the highest frequency will be the red wave. The highest wavelength is the red wave, right? So he'll have a red shift of light, and Daniel will have they don't call it the violet shift, they call it the blue shift, because reasons. There's blue and there's red. So if it moves to the left, it'll be red. Moves to the right, it'll be blue shift. So that's a blue shift. So Daniel will see more of a blue tinge coming in, and David will see like an orange, yellow, orange, red tinge. But they're both looking at the same light source. So that's the idea here. It's the same as sound. It's just instead of sound, we're not looking at pitch, we're working with colors. All right. Now, looking at absorption spectrum and lines, so let's read this quick. If you pass current through an element in a gaseous state, or if there's a very high temperature on stars, the electrons move up and down energy levels, and they release energy as light when they come down a level. And this light can be broken up with a prism, and this will result in an absorption spectrum, which is this thing. And because, it's called an absorption spectrum because some of the frequencies will be absorbed by the gas. So it depends on the element. So I wrote here, Dependent on the element in the gas phase, it will absorb certain frequencies or certain parts of the color, which will make these little gaps in our Roy-G-Biv situation. So just take a look at that. Roy-G-Biv is backwards in these absorption spectrum diagrams. So if we are here on Earth and this star is moving away from us, as you saw just now, it will be if it moves away from us, we'll have higher frequency. You'll see a higher frequency. Yeah, so yeah, I did on purpose. A higher wavelength, higher wavelength, which will result in a lower frequency, which will then result in, is it blue or red shift? We have a high wavelength, low frequency. Let's take a look. Higher wavelength, lower frequency, red shift, right? Red shift. And going away, that side obviously is a blue shift. We have a smaller wavelength and a higher frequency, which will be the blue shift. Quite straightforward, quite simple. And we speaking about these absorption spectra or diagrams. The same will hold true looking at this diagram here. Earth, if the star is moving away, we have a red shift, which means that these, let's just say this is the absorption lines. They will actually change like this. They'll shift towards red. So the absorption lines will shift nice and symmetrically towards the red side. If it's a red shift, this will be a red shift. So let's take a look at some examples. We have a sun spectrum and a star X spectrum over here in the middle. And the sun spectrum looks like this, and the star X spectrum looks like this. The sun is stationary, right? So it's stationary, and star X will be moving. Now the question is star X moving away or is moving towards the Earth or the sun or whatever? So that's the question. How do we determine this? Well, we know there's a shift. If we take a look at the lines we drew here, the absorption lines, they're being shifted to the left. They're being shifted towards the blue side. They're being shifted towards the blue side. We have a blue shift. And what does that mean? It means that if it's a blue shift, I remembered this because red wave, right? But it will shift towards the blue or the violet side. So we have a lower wavelength and a higher frequency. So best way to remember is just to draw two observers, draw your light source in the middle, and we can look at this guy here. And if it's going this way, we will have a higher frequency and a lower frequency that side. So the person on the left will have a lower frequency and a higher wavelength, and the person on the right will receive a higher frequency and a lower wavelength. Now, if you're looking at this, we know that if we have a blue shift, it will be the one with a lower wavelength. So it will be this side. So this star X is moving towards the Earth. Okay, so towards the Earth or the observer. Let's look at the second example. We have the same sun spectrum, and then we have star Y. Now there's a shift towards the right? So this is now to a little bit to the right, and that is shifted a little bit to the right. So we have a red shift. So red shift. So it's a star Y moving towards the sun, away from it, towards the Earth, away from it. So what we have to know is that we have a red shift. A red shift, and red being the high wavelength and lower frequency, and blue indigo violet being the lower wavelength and the higher frequency. So a red shift, a shift towards the red side. A shift towards the red side will end up with the higher wavelength and lower frequency, and the shift towards the violet side, we end up with lower lower wavelength. So we're shifting towards the red side. Shifting towards the red side. So if we're shifting towards the red side, we're going to look where the higher wavelength, lower frequency part of it is, and that will be where the wavelengths, yeah, we said high and low, so obviously then the thing has to be moving to the right, which is then away from Earth or observer. Right, so it is going away, away. So redshift is away from Earth observer. Yeah, so to sum it all up, I'll draw something quick for you guys. Right, so here's a little summary. Wait, I'll add another picture. Alright, so taking a look at this little summary diagram I drew. So the light source is traveling to the right, and looking at the person from the left is how he perceives the light source. You have a low frequency, high wavelength, and that's called the red shift. And that'll be in terms of color and the absorption lines, and that's it moving away from the person. And the opposite is true for the person on the right. The high frequency, low wavelength, the blue shift in terms of color and the absorption lines, and that's because the light source is moving towards. Now I also drew another, let's just watch you both backwards, so just watch out. So there's that little summary block again. If you have an original sort of frame of reference and these lines shift to the left, it will be towards the violet side or the blue side. So you have a blue shift, it's towards the observer, which means you have a high frequency and a low wavelength. And if it's shifted to the right, we have a red shift. To the right is red, and it's away from the observer, and you have a low frequency, higher wavelength. There we go. Hope that helped you guys. Please like and subscribe, and tell Kelsey to put a blazer on in the corridors. Very important. Where's Kelsey? I lost her. Oh, there she is. Blazer on in the corridors, Kelsey, and cut your nails. Damn it. Every time.